Welcome everyone to the video lectures for electromagnetic course. In this video, we will discuss about plane wave in good conductors. We consider electrical properties such as conductivity and permittivity of a good conductor and realize and rewrite the Maxwell's equations for such regions. Then the wave equations will be derived and solved. To derive the field expressions in time domain and in frequency domain. If we inspect the water wave, you will see the wave propagates on the surface and also penetrate into the water. The amplitude of the wave decreases as it penetrates into the water. Similarly, electromagnetic wave can propagate around the surface of a conductor, also can penetrate into the conducting region. Look at the figure below. You can see a conducting region sandwiched between air regions. An electromagnetic wave is traveling from air to the conductive material and then released to the air. The strength of the wave will be attenuated while it travels through the conductive region. The phenomena of decaying of the electromagnetic wave strength is called skin effect. We rewrite the Maxwell's equations for a linear, homogeneous, source-free, isotropic conducting medium. The Maxwell's equations that we obtained here are very similar to those what we obtained for lossy dielectrics. We define effective permittivity in the same way as we did for lossy dielectrics. Also, the wave equations that we obtained in the lossy dielectrics are very similar to the conducting regions. If you look at the wave equations here, that is del square Es minus gamma square Es equal to 0 in terms of E field, and if you write them in terms of H field, that will be del square Hs minus gamma square Hs equal to 0. Where gamma is the propagation constant, the expression of gamma is same that we have learned for lossy case. If we solve the wave equation for one-dimensional case with in terms of E field that is propagating in Z direction and polarized in x-axis, you will come up with the solution of Es equal to Ex0 e to the power negative gamma Z Ax. The only dissimilarity of a conducting material from a lossy dielectric is the conductivity of a conducting material is much higher than dielectric material. Let us consider a good conductor, for example copper. The conductivity of copper is 5.8 times 10 to the power 7 Siemens per meter. If we assume a high frequency electromagnetic signals of 100 megahertz, then the factor sigma over omega epsilon is equal to 1.04 times 10 to the power 10. So meaning that sigma over omega epsilon is much larger than 1. So the term of propagation constant inside the square root 1 plus sigma over j omega epsilon, we can approximate this with only sigma over j omega epsilon because this value is much bigger than 1. So if you add 1 with this number, so the value will not change. So we write it like square root of j and we can cancel out epsilon. We'll come up with square root of j. The expression you see here, square root of j and square root of omega mu sigma, and square root of j can be transformed to 1 plus j over square root of 2. I show you the work here. In j can be written with Euler's equation like e to the power j pi over 2. Now, if you take a square root of j, you can write it e to the power j pi over 4. If you take a square root here, the phase angle will be 1/2. So that is cosine pi over 4 plus j pi sine pi over 4. So cosine pi over 4 is 1 over root 2 and sine pi over 2 is also 1 over square root of 2. So you can write it like 1 plus j square root of 2. So we substitute square root of j with this number. So that's we put it here, and then omega we can write it like 2 pi f mu sigma. That becomes 1 plus j square root of, so if you cancel out the square root of 2 here, that should be pi f mu sigma. And it got a real part and an imaginary part. So we write the real part alpha and imaginary part beta. So now alpha and beta got the same magnitude, that is pi f mu sigma square root, and we substitute alpha and beta with one variable that is called 1 over delta. This delta we can define it like the skin depth. We can define this delta as a skin depth. So we are going to discuss about skin depth in the next slide. So let us find the wave impedance here. The wave impedance eta, or the formula like a square root of mu over epsilon e, and epsilon e, we know the formula is epsilon times 1 plus sigma over j mu epsilon. As we see, this term is very large in comparing to 1, so we can approximate this term by removing this 1 and then cancel out this epsilon with this epsilon and pushing this omega on the top. So you'll get j mu omega and sigma. So here you see this is an imaginary component with magnitude omega mu over sigma. So the amplitude is omega mu over sigma, and a square root j is 90 degrees. If you take a square root of the j, that will be 45 degrees. So in polar form, the intrinsic impedance has the value of magnitude is square root of mu omega over sigma, and the phase angle is 45 degrees. So now if you substitute omega with 2 pi f, so then we can simplify this expression square root of 2 mu pi f, and we multiply sigma, square root of sigma, in both denominator and numerator, and then this section, this value is basically the skin depth. So we can write square root of 2 over sigma times the skin depth delta angle 45 degree. So the expression we obtain here is the intrinsic impedance for good conductor. Now if you want to find the speed of propagation, a good conductor, the wave will propagate with this speed, omega over beta. As you know, we write beta equal to 1 over delta, so you can write omega delta. And the wavelength lambda, we can write in terms of 2 pi delta. So all the variables, parameters, basically for good conductor, we replace them with respect to the skin depth. We rewrite the electric field intensity with respect to the skin depth. The electric field expression E, the time domain, can be written as Ex0 e to the power negative z over delta. This is the attenuation factor 1 over delta. Cosine omega t z over delta. So this delta 1 over delta is the phase constant, and the wave is polarized in x direction for this case. And if we want to find magnetic field intensity vector, we can apply the formula 1 over eta AP cross ES, and we replace eta with mu epsilon over sigma, and the wave is propagating in this case in positive z-axis, and we can write it like Ex0 in the frequency domain. It does it. So the S field will be sigma mu epsilon Ex0 e to the power alpha z cosine beta z for minus 45 degrees. So only the difference from lossy dielectric and good conductor is, in good conductor this angle is 45 degree, but for lossy dielectric the angle was psi eta. So on this slide you can see the electric field, magnetic field and current distribution in a conducting region. So in the figure here you can see if the electromagnetic wave incident from the vacuum or free space or air to a metal, it will get attenuated, the magnitude will get decreased. So if you draw a graph showing the maximum points of these waves, the envelope of this graph is an exponentially decaying graph, E negative z over delta, where delta is the skin depth. So if you plot this graph down here, you'll see the delta. If you put delta equal to z, so then this value will be e to the power minus 1 or 1 over e. 1 over e is equal to 0.368. That means 36.8%. So at z equal to delta, the amplitude of the electric field or magnetic field or current will be 36.8% to the initial value. So if the incident wave has a magnitude of 1, then the magnitude will reduce to 36.8% of the initial value at a distance z equal to delta. So the skin depth is defined as a distance where the electric field or magnetic field or current magnitude is reduced to its 36.8% of the initial value. That is called the skin depth. Now, if you see the skin depth of copper, you can find that at 10 gigahertz frequency, the copper skin depth is 0.661 micrometer. So this information may be important for designing a waveguide or a guided structure or electromagnetic shielded room. So at 10 gigahertz, for waveguide, if the operating frequency is 10 gigahertz, the wave will reduce to 36.8% if penetrate to 0.66 micrometer. Therefore, the skin depth is an important measure to determine the thickness of waveguide wall so that the radial power radiation remains low. So if you want to make sure the radiation coming out of the waveguide to a low level or EM radiation from the device, if you want to reduce the EM radiation of the device, you have to the thickness of the metal casing properly by knowing the skin depth. And also for low frequency like 60 Hz, the thickness will be 8.53. So the EM energy is not transmitted in the interior. The EM energy is not transmitted in the interior of conductor. However, EM energy, electromagnetic energy, may travel in the region surrounding conductors or surrounded by the conductors. So the EM energy travel in the region surrounding conductor. If it is low frequency, or EM energy can be transmitted through a waveguide that is surrounded by a conductor. So we can use a hollow structure to carry the electromagnetic energy, or a solid structure to carry the electromagnetic energy. So in particular case, just for low frequency we use solid conductor. For high frequency we use waveguide or optical fiber. So skin depth or penetration depth is defined with the term delta, and it is the distance at which the amplitude of electric field or magnetic field or current density drops within a conductor to 36.8% in relation to their values at z equal to 0. Look at the figure here. It shows the skin depth for current densities in steel. So at low frequency like 60 Hz, the skin depth is 6 inches. So the electric field, magnetic field or current can uh, penetrate through the radial direction up to 6 inches. And for like 1 kilohertz signals, the depth is goes to 0.2 inches, like 5 millimeter. And if you go for 400 kilohertz, the thickness is only 0.75 millimeter. If you design a circuit for high frequency, you can use a hollow pipe like this. So you need only 0.75 millimeter thick walls, so that the electric field cannot go outside of this wall, or you can get the system reflection free, because your electromagnetic wave will be confined in this region. But if you want to go for a power circuit design, then you have to make the conductor solid and choose the radius of the conductor properly. So in designing the thickness of steel wire for low frequency circuit, you can determine the thickness of the wire by knowing the skin depth. At 60 Hz, the depth is 6 inches or 150 millimeter, which is an important measure to determine the radius of a power cable. As you know, the resistance of a cable is inversely proportional to the cross-sectional area, more specifically the radius of a solid circular wire. If we design a thick wire, the resistance of the wire will low, and the power loss inside the wire will be low. But after some extent, the increase in radius will not be useful, as electric magnetic field and current are distributed around the surface of the conductor because of the skin effect. So if you go in this case, if you go or design your wire more than 150 millimeter thick, that will not be useful or effective anymore, because the signals cannot penetrate more than 150 millimeter. Now we want to calculate power density or Poynting vector for a good conductor. So the time average power density vector or Poynting vector for a conductor, let us given the electric field expression Es and the magnetic field expression Hs, like this. Now to get the time average power, we know the formula is half real Es crossed Hs conjugate. So we need to find Hs conjugate first. So to get Hs conjugate, we have to replace the j term, sign of the j term to the opposite, like negative j becomes positive j. Here we have negative j, it becomes positive j. So now we do have the electric field expression and the conjugate of magnetic field expression. So if you multiply this, you will get the sigma delta over square root of 2 ex0 squared e to the power 2 negative z over delta, and here this j and this j term will be cancelled out because this is positive, this part is negative, but we have 45 degrees, so e to the power j 45 degrees. So now if you say this part has the imaginary component here e to the power j 45 degrees, so if you expand this, it will be cosine 45 plus j sine 45. So we take only cosine 45 degree. Cosine 45 degree is equal to 1 over square root of 2. So 1 over square root of 2, and here we get 1 over square root of 2 becomes 2, and 2 and 2 is 4. So we got 4 sigma delta ex0 square e to the power 2z az. So this is the time average power. Now if you want to find power at z equal to 0, you see the time average power is z equal to 0 will be sigma delta 4 ex square az, and time average power at delta at the skin depth, the expression will be like this. So if you replace this expression with here, you'll see this is equal to e to the power negative 2 times of the 0 power, so at the surface power. So power at the surface is this, power at the skin depth delta as this. So the power reduction decrease, power attenuation at the skin depth will be 13.6 of the surface power. So that means at the skin depth, the electric field will reduce to 36.8%, but the power will reduce to 13.6% of the initial power. Here we will show you how to calculate the electromagnetic power in good conductor. So to calculate the power, we can apply three different methods. So here the first method is using pointing vector and compute the power crossing a closed surface. So let us think there is a transmitter that transmitting power through this waveguide. The waveguide got a dimension. This side is A, and this side is B. So the length of this is B and height of this waveguide is A, and through this surface the signal is coming in, entering into the system. So we want to find how much power is flowing through this surface in per unit time. So we are going to find the time average power here. To calculate the time average power, we need the expression for electric field. So let us assume the electric field expression is given like this. So in you see the power is flowing the z direction because the wave got the expression. From this expression you see the electric wave is moving in the z direction. So to find this, we need to find the power, time average power. Time average power expression is this one. So that we obtained before, sigma delta over 4 e to the power x0 square to e to the power negative 2z over delta az. This expression we found in the previous slide, so we choose that expression. And from this, if we don't provide you this expression, so you have to start with this electric field, then find the magnetic field, and then conjugate of magnetic field, then you can get this expression. So from this expression we put this value here, P average, and the surface integration ds over the closed surface S. So This surface integration, basically this side is dy, this side is dx, so we write dx dy, and the x is from 0 to a, so integration 0 to a, and y we integrate from 0 to b, 0 to b, and we integrate this, and we will get the power loss in this system is delta sigma 4 ABEX0 square in this method. So in this method, we are measuring how much power is flowing out of a surface. So here we know the closed surface, and we are determining the power, calculating the power flowing out of this surface using the Poynting vector. And the second formula is power calculation using considering the Ohm's law. You know, I square R is the power loss. So here we are using the Ohm's law, point form of Ohm's law, Z dot E dV, the volume integration of Z dot D dV. So here you see we are finding how much power will be lost by the system. So J is sigma E, so we write sigma E times E, and dV is dx dy dz. The variation of x is from 0 to a, y is from 0 to b, but z could be 0 to infinity because we don't know how long the system is. So we write 0 to infinity, and then we solve this integration in term. So this is exy square is the constant term, so we bring it left, sigma, and the integration of x will be a, integration of y will be b, and we integrate this with respect to z, and you get this value. So this is sigma delta over 4 abx square. So this is the very same thing that we obtained before. So the previous case we obtained using uh, Poynting vector, and now we finding the ohmic loss, so the conduction current loss. And the third method is finding the power using assuming using the I square R formula. So to find I square R, we need to find the current first. So to get the current, we need current density Js over ds times ds, and J is sigma times EDS. So we solve sigma times EDS, and ds is here dy over dz, because E is you say the E has a direction ax, so our ds should be has the same unit vector ax, so we write dy dz ax, and we find the as now. So total current flow in AS, I equal to this. So find I, and we integrate this. We'll get the expression for I is AB EX0 delta on plus J. Now we find the magnitude of this. So AB delta X0 delta, and magnitude of this part. This is the in rectangular form. So in polar form it will be 1 plus 1 square. 1 square plus 1 square square root, so that is 2. Angle is negative 45 degrees, but we don't consider the angle, we just taking the magnitude of current. So this is the magnitude of current, then I solve for is square, because the formula require is square times r. We are taking half because this is the maximum value. We are taking is over this, but we need to find the RMS value, so we just divide this with out of our square root of 2, that we did here. Sorry, so we got is square like this. Now we use the formula half is square times r, and r is the resistance of the system. So we can find the resistance by taking the skin depth. Delta b is the cross-sectional area. This is the conductivity, and A is the length. So we are taking A is the length, and delta B is the cross-sectional area with respect to the skin depth and delta. Now substituting the R values, we can find the power loss.